All right, so now I'm going to talk about boundary value problems and how one can try to discretize this using the method of finite differences. Okay, so let's start with the problem formulation. So you have a boundary value problem of the form of a second order differential equation over some intervals, say from 0 and 1. And you have boundary conditions, y at 0 is equal to alpha, and y at 1 is equal to beta, for example. And then what you can do, of course, is you can consider some sort of partitioning. It's like of the interval from 0 to 1. Let's just say it's uniform. So let's consider uniform partition. Of the interval from 0 to 1. Okay, and so you have xj, for example, is equal to j times h, and j goes from 0 to n plus 1, and then h is 1 over n plus 1. Okay, all right, so again, you have some sort of interval from 0 to 1. This is going to be x0, this is going to be x n plus 1, and then they're uniformly spaced sort of points xj, it's like between them. And then we're going to assume that you have corresponding, it's like y values, let me call them y sub j. Okay, so we want yj to be some approximation of y at the time, well, at the position xj. Okay. All right, so with this kind of setup, we would like to write down a system of equations. It's like for the yj's, basically, which they satisfy. Okay. So I want to write down system of equations. For the yj, whose solutions sort of approximate the solution of the boundary value problem, right? So one way, of course, to do this is to try to approximate this second derivative operator. And particularly, you can do this using some sort of symmetric finite difference approximation. So for example, so we can approximate the second derivative, sort of d squared y dx squared by finite differences. Okay, so for example, d squared y dx squared is approximately equal to y at x plus h minus 2y at x, right, plus y at x minus h divided by h. And you can see that this is a reasonable approximation of d squared y dx squared at the point x. If you do a Taylor expansion of these terms about x, it's like, and then see what happens. Okay. All right, so with that in mind, I'm going to replace this derivative using a finite difference. Okay, so I'm just going to leave the boundary value problem up there. Maybe I'll write it in a corner here. Okay, so we have d squared y dx squared is equal to f of x. X is between the interval from 0 to 1. And then we have boundary conditions. Y of 0 is equal to alpha, and y of 1 is equal to beta. Okay. All right. So what I'm going to do is I'm going to approximate that second derivative term using a finite difference. So I'm going to have d squared y dx squared at the point xi. Maybe let's call that xj. Okay, xj is going to be approximately equal to y at j plus 1 minus 2y at j plus y at j minus 1. So that's sort of corresponding to this thing here, divided by, I'm sorry, there's a h squared here. All right, divided by h squared. Okay, yes. Right. And then it's like you have this f at x, right? So I denote this evaluation, right? So I'm going to denote by f sub j, f evaluated at the point xj. Okay. So, all right. So that gives you, so with those two things in mind, it's like what happens then is that you can rewrite, or you can replace, it's like the differential equation by the following. You can write that yj plus 1 minus 2yj plus yj minus 1 over h squared is equal to fj, right? So this becomes an approximation of that first equation here, which is the differential equation. And then it's like the boundary conditions y0 and y1, if you recall. So the other thing, of course, is that xj is equal to j times h, and then h is 1 over n plus 1. So it's easy to convince yourself that x0 is equal to 0, and xn plus 1 is equal to 1, right? So with that identification in mind, right, you can replace these boundary conditions by saying that y at 0 is equal to alpha and y at n plus 1 is equal to beta. So now that system of equations is an approximation, if you will, it's like of this boundary value problem. And if you could solve this you've already prescribed y0 and yn plus 1, so you really need to solve this for y1 all the way up to yn, right? So we wanted to solve this for y1 to yn, okay? And so you might ask, well, how did the boundary conditions here come in? And the way to sort of see this, if you look at this equation, so you want this equation to hold for j is equal to 1 to n, basically. Okay, so if j was equal to 1, it's like then this equation in particular would involve y1, y2, y1, and y0, right? So you need the y0, it's like from the boundary data, okay, in order to write down the system. And then similarly, if you have j equals to n, then this would involve yn plus 1, yn, and yn minus 1. So you need the you need the yn plus 1 term here. It's like corresponding to beta. Again, it's like to write down that equation. Okay, so that's where the boundary data enters into that system of equations. Okay, so let's see how that happens. So let's try to, again, write down this system. Okay, so you want to solve this for y1 to yn. So let's denote that unknown. It's like by some vector y, which is a vector from y1 to yn. And let me try to write this now as a as a linear system of equations. Okay. So I'm going to rewrite this particular equation a little bit, okay, just so that the coefficient associated with the yj is -1 instead. Okay, so I'm going to write this as 1/2 yj plus 1 minus yj plus 1/2 yj minus 1 is equal to h squared over 2 fj. Okay. All right. So I can write this thing down in the following way. Okay, so I can have a matrix A, which looks like -1, 1/2, 0, 0, 1/2, -1, 1/2, 0. Okay, so again, this coefficients correspond to these entries, right? And then let me just write down the last two, 0. Okay, so there's a 1/2 -1, and there's a 1/2 here, right? Goes up to 0 here, and there's a 1/2 and -1. Okay, so you can sort of see that what happens is that you have a diagonal of, let me just move this down a bit so that it looks a bit clearer, right? You have a Okay, so you have a diagonal of -1s, and then sort of these, you know, it's like, so the main diagonal, it's like has -1s, it's like, and the one just above it, it's like has 1/2, and the one just below it is like has 1/2 as well. Okay, again, it's like those coefficients just come from this equation, sort of this equation here, and then the right-hand side, f, okay, is going to, as you might expect, it's like involve these h squared over 2 fj terms, right? So h squared over 2 f1 all the way up to h squared over 2 fn, okay? But if you look at this, right, we are sort of missing something, right? Because we had talked about, well, what happens at the j equals 1 and j equals n case. So the j equals to 1 case, it's like involves a y0 term, which we use the boundary data for, okay? And so the essence is that because this linear system of equations which we're going to set up, right, doesn't only involves, it's like y1 to yn, it's like you can ask, well, where's the y0 and yn plus 1 terms going to come in? And they're basically going to come in, it's like on the right-hand side of the linear equation, okay? So in particular, it's like when j is equal to 1 here, this is this 1/2 y0 term. I'm going to move that to the right-hand side. Okay, so there's a -1/2 y0 term. It's like for the very first equation. So this is -1/2 alpha. And then similarly, for the line corresponding to j is equal to n, right, there is going to be a 1/2 yn plus 1 term, which again, I'm going to move to the right-hand side. So this becomes -1/2 beta. Okay, but everything else in the middle, it's like just, with the exception of these boundary terms, right, just involves these 1/2 fj terms. Okay, so all right, so with this kind of identification set up, right, then this set of equations, both the equations j equals 1 to n, as well as these two boundary data, right, can be incorporated into a linear system involving n unknowns, right, but where the boundary data, it's like, again, ends up showing up on the right-hand side instead. Okay, so this now looks like just ay is equal to f, so you just have a linear system here for these values of a and f. Okay, all right. So what's special about this is that this is what's called a tridiagonal system, right? So this is a system of linear equations. It's like where it's like the this matrix A is a tridiagonal matrix. If you recall, it's like from your course on numerical linear algebra, it's like then what happens with tridiagonal matrices is that it's possible to use, it's like a form of LU, it's like which is very efficiently computed, which allows you to factorize this matrix A, it's like into sort of LU form very efficiently. So that's not the only way, but that's sort of a very sort of natural way to do this. Okay. All right, so maybe I should. Yep. Okay, so anyway, so the remark is that this matrix A is a tridiagonal matrix. Right, so you can factorize this sort of easily using LU, right? So you can do, once you have LU, then you can use, it's like, it's like back substitution to solve this system of equations. Okay. Sort of can solve this system sort of easily. Okay. So, all right. So that's of course sort of the very special case. It's like where the differential equation just involves the second derivative. It's like an f on the right-hand side, which only depends on x, right? So let's look at the more general, well, more general linear case. Okay. So let's see what happens. So let's consider the more general, the general linear case. Okay. And you should imagine that you could also do this for nonlinear boundary value problems, right? And the usual thing that's like one does, obviously, when dealing with nonlinear problems in the context of numerical methods, is to take the nonlinear problem, linearize it, it's like solve the linear problem and then use that in some sort of iterative way. It's like to, hopefully, it's like converge to the solution of the nonlinear problem. Okay, so even if you had a nonlinear system, it's like the standard mechanistic way of approaching this problem is to linearize it and then solve the corresponding linear case. It's like exactly, it's like, well, not exactly, but with this kind of approximation, for example, and then you have to iterate. Okay, so nevertheless, the looking at this general linear case is relevant for that problem. So. So if you have y double prime is equal to f of x, y, and y prime, right? And it happens to be, it's like linear, in which case you can write this as u of x plus v of x, y of x plus w of x, y prime of x. Okay. Then we already saw it's like how you can do a approximation of the second derivative, right? So now you're going to have to approximate the first derivative as well. And again, it's quite natural to do that approximation in some sort of symmetric way, some central difference. Okay, so I can approximate the second derivative, the first derivative. Using finite differences again, using sort of central finite differences. So y prime of x, right, is going to be y of x plus h minus y of x minus h over 2h. And if you did that, you would get something which was second order accurate. Okay. So with that in mind now, I can write this equation down, right, as yj plus 1, or I can replace that by this approximation, yj plus 1 minus 2yj plus yj minus 1 over h squared, right? This is, again, an approximation of the second derivative, is equal to f at xj, yj, and then yj plus 1 minus yj minus 1 over 2h, all right? Okay, so that's sort of this general form so far. We're going to assume that that right-hand side is linear, okay, in y. So this looks like uxj, which I call uj, okay, plus vj yj plus wj yj plus 1 minus yj minus 1 over 2h. Okay, so now it's like I can collect the coefficients involving yj, yj plus 1, and yj minus 1, okay, in the following way. And before I do that, I'm going to multiply throughout by h squared, actually minus h squared. So I'm going to multiply by minus h squared and collect terms. So in doing that, it's like in collecting all the coefficients involving, well, all the terms involving the yj's in some sense, you end up getting minus 1 minus h over 2 wj, yj minus 1, right? Because I've multiplied by minus h squared, right? So this becomes a plus 2, and this becomes a minus, right? So there's a minus 1 here. And then because I've multiplied these terms involving the yj minus 1s and yj's again by minus h squared, right, you get this minus h squared wj term. Okay, plus 2 plus h squared vj yj plus minus 1 plus h over 2 wj yj plus 1 is equal to minus h squared minus h squared uj. Okay. All right, so let's call these things something. Let's call this a j minus 1. Let's call this dj. And let's call this cj. And let's call this whole thing bj. Okay. So maybe let's write that down somewhere. Okay, so aj minus 1 is equal to minus 1 minus h over 2 wj. dj is equal to 2 plus h squared vj. And then cj is equal to minus 1 plus h over 2 wj. And then bj is equal to minus h squared uj. Okay. Then I can rewrite the finite difference approximation of this more general linear case, right, in following way. And then, of course, you have the usual boundary conditions. Y0 is equal to alpha, yn plus 1 is equal to beta. Okay, so in this notation, we have the following system for the general, for the finite difference approximation of the general linear. It's like boundary value problem, right? So, okay, so it looks like the following, right? So you have d1 to dn as before. You have a c1, and then, well, c1 to cn minus 1, and then zeros. Okay. All right, and then you have a1 to a n minus 1, and then you have zeros again. Okay, so you have a linear system like this, and then, well, you have a matrix like that. It's like, and then y1 to yn. So this part is fairly similar to the case before. And then you have the right-hand side be 1 to bn as before, and again you have to include the boundary data. Okay, so you have b1 to bn, and then if you recall, it's like we also incorporated the boundary data. It's like on the right-hand side, but because now these coefficients are more complicated, it's like that correction involving the boundary data involves these a and c coefficients. Okay, so minus a0 alpha here. Okay, I'm going to write this as b2 to bn minus 1, and then the bn term involves a minus cn beta. Okay. So again, all this is sort of fairly straightforward. You just have to, it's like going up to this point is fairly straightforward. It's like, and again, it's like this right-hand side, it's like involving the alphas and betas. It's like for the n equals to 1, sorry, the j equals to 1 and j equals to n case, right? That just comes from writing down, it's like these equations for j equals to 1 and j equals to n. It's like, and then using the fact that y0 is alpha and yn plus 1 is beta. Okay, and then it's like whatever term involves the alpha beta, it's like you move to the right-hand side, and that's where you get these correction factors, which involve the boundary data. Okay, so right. So anyway, so that's how you set up a boundary value problem. In particular, the general linear case, right, using this method of finite differences. Okay, using central finite differences. So let me just stop here for now and then we'll talk about the properties, it's like, of the solution in a little bit. Okay.